So, hello everyone. Today we will be discussing our project titled Devising Career Recommendation with Neural Pair Collaborative Filtering. I am Abhishek Gautam and I have worked on this project with my teammates Ayush and Haribhajan. Our goal was to develop a recommendation system that not only provides accurate recommendation but also addresses biases that may affect fairness, especially in the career recommendation. So to start, let's quickly go over what recommendation system do. Recommendation system are widely used across platforms from streaming devices like Netflix, Spotify to e-commerce website like Amazon. They use collaborative filtering, leveraging user preference to make personalized suggestions. However, one key issue is that these systems can often perpetuate biases found in the data, leading to unfair recommendations. For example, in career recommendations, certain roles or industries might get unfairly associated with specific demographics. Our project is focused on addressing this challenge using neural pair collaborative filtering, in short, NFCF. NFCF aims to reduce bias in recommendation while maintaining high accuracy, balancing the need for fairness with practical usability. Let's have the overview of the mode cloth dataset. So we will be using the mode cloth dataset to evaluate our model. Mode cloth is the dataset which rich information on user item interaction, specifically in the fashion industry, and it includes sensitive attributes like body shape, categorized as small, medium, and plus size. This dataset is known to exhibit bias as recommendation system often favor the majority demographic. In this case, small body shapes. Our goal with NFCF is to mitigate this bias, ensure that recommendations are equitable across the different body size. So here how we use the dataset in NFCF. Pre-training. We initialize user and item embedding based on non-sensitive interaction. Embedding debiasing. By identifying the By identifying and removing bias component, we could make sure the embedding are not aligned with the body shape attributes. And the third is fine tuning. We use fairness penalties to ensure the model provides equitable recommendation across the different body shapes. These steps allow NFCF to handle demographic disparities in recommendation effectively.
Now let's talk about the methodology. NFCF incorporates two main components: embedding debiasing. This step involves removing bias in embeddings. Specifically, we project the embeddings orthogonally to the bias vector, which reduces alignment with sensitive attributes. Fairness penalty. We introduce a fairness penalty term in the loss function aiming for demographic parity. This means the model is encouraged to treat different demographic group equally. Our training process has three stages. Pre-training. This stage involves learning robust embeddings from user item interaction. Embedding debiasing. Here we adjust the embeddings to remove any bias components. And fine tuning. Finally, we optimize the model using sensitive attributes and fairness constraints. To measure the performance of NFCF, we use two categories of metrics: fairness metrics and accuracy metrics. Fairness metrics, we have differential fairness, which measures recommendation parity across groups, and absolute unfairness, which quantifies the discrepancies in predictions between different demographic groups. In terms of accuracy metrics, we had hit ratio, which evaluates if relevant items appear in top 10 recommendations, and NDGC, which weights the ranking quality of recommendations, favoring relevant items ranked higher. Using both fairness and accuracy metrics help us to ensure that NFCF doesn't improve fairness but also maintains practical recommendation performances. We visualize the embeddings to see the impact of debiasing. The PCA projection before debiasing showed strong clustering along body shape attributes, indicating bias. After debiasing, clustering was significantly reduced, suggesting diminishing bias in the latent representation. In terms of performance, NFCS showed remarkable results on mod closed dataset compared to the baseline model. The HR10 and NDGCG10 were significantly improved, indicating better recommendation accuracy. Differential fairness and absolute unfairness values were much lower in NFCF, demonstrating improved fairness across groups. This shows that NFCF can achieve a balance between fairness and accuracy, outperforming baseline models on both fronts.
Coming to the fairness-accuracy trade-off, one of the most interesting findings was the fairness-accuracy trade-off. NFCF successfully managed this trade-off better than the baseline models, maintaining high accuracy while significantly reducing bias. This is crucial for real-world application, where sacrificing too much accuracy for fairness would make the recommendation system less effective. Debiasing embedding visualization. To further illustrate the debiasing process, we visualize the average embedding for small and plus-size groups, both pre and post debiasing. This visualization shows that after debiasing, the embeddings for different body shapes are less aligned along the bias axis, indicating that NFCF has successfully mitigated demographic bias. Coming to the conclusion and future ideas. In conclusion, NSCF has proven to be an effective framework for addressing bias in recommendation system, as demonstrated on the mod-cloud dataset. It mitigates bias by debiasing embeddings and adding fairness penalties without significantly compromising accuracy. This framework can be applied in various fields, including career recommendation, to ensure fairer treatment across demographics. Thank you for watching our presentation on neural fair collaborative filtering.